Hello everyone and welcome to this short presentation of our paper Graph Embedding in Vector Spaces using Matching Graphs. My name is Mathias Fuchs and my co-author and supervisor is Kaspar Riesen, and we are both from the University of Bern in Switzerland. Okay, first I will start with a few definitions that are necessary in order to understand our approach. The most basic one is the definition of a graph. You can see here the formal definition, but intuitively speaking, a graph consists of a set of nodes and a set of edges, whereas both of them can contain additional attributes. On the bottom left here, you can see a graph with additional node attributes, and on the right, you can see a graph without any additional attributes. Next up, the definition of a subgraph. Here again, you can see the formal definition, and intuitively speaking, a graph G1 is called a subgraph of G2 if all nodes and all edges of graph 1 are contained in graph 2. Here you can see a few examples. Let's say we have the base graph, graph 1, and then here graph G2 would be a subgraph of G1, and as well as graph G3 is a subgraph of G1, but obviously not of graph G2. Next up is the definition of a graph isomorphism. So two graphs G1 and G2 are called isomorphic if there is a matching part for each node and each edge of graph 1 in graph 2 and vice versa. And then very closely related to this is the subgraph isomorphism. A graph G1 is subgraph isomorphic to a graph G2 if there exists a subgraph, let's call it G, that is a part of G2 that is isomorphic to G1. A few examples here of the subgraph isomorphism or graph isomorphism. Let's say again we have the same graph G1 and then graph G2 and graph G3. So G2 is isomorphic to G1 and G3 would even be subgraph isomorphic to G1. Graph and subgraph isomorphism problems are exact graph matching problems. However, there are also inexact graph matching problems. That's, for example, when exact matching is impossible. And the goal is to find just the best possible match. Over the years, various of these procedures have been proposed. Some of the most known ones would be graph kernels, spectral methods, graphite distance, or graph neural networks. In our work, we used the graphite distance and focused on it. So, what is graphite distance? Given two graphs, G1 and G2, the basic idea of the graphite distance would be simply to transform graph 1 into graph 2 using a given set of edit operations. In our case, or the default set of operations are usually insertions, deletions, and substitutions, and those operations can be done for nodes and edges similarly. However, there are also other operations that are possible, but for our work we use those three operations. Here we can see a quick example of the graphite distance and the corresponding edit path. On the left here you can see the source graph, and on the right you can see the target graph. And down here you can see the corresponding edit path. Denoted like this, for example 0 to 0 are all the substitutions, meaning node 0 in the source graph got substituted with node 0 in the target graph. Denoted like this, 5 to epsilon, for example, are the deletions, meaning that node 5 here from the source graph didn't get a match in the target graph, hence it is deleted. And denoted like this here, for example, epsilon to 5 means that here node 5 is inserted in the target graph because there was no counterpart in the source graph. Standard procedures to compute the exact graphite distance are of combinatorial nature and are hence of exponential complexity. In our work, we only use an approximation for the graphite distance, so we do not calculate the exact graphite distance, and the algorithm we use for this is the Bipartite graphite distance algorithm, and it is denoted by dBp from now on. Okay, now that we have done all the definitions that are necessary, I will start with the general idea of our approach. So the general idea is that we pre-compute matching graphs. I'll tell you in a second what they are on a given training set, and we then use those matching graphs to represent a given graph in the form of a binary vector, and this is done that the vector contains 1 if a matching graph occurs in this graph and 0 otherwise. And in the end, we intend to use this vector representation for classification purposes. Okay, so what are these matching graphs? The general idea is to build like a small set of graphs that are able to represent a certain class, and we build those matching graphs by formalizing the information of a given edit path between two graphs Gi and Gj in a new data structure, which we call the matching graph. And it's important to notice that for each edit path, Gi to Gj, two matching graphs are built, so one from the source graph towards the target graph, and one from the other way around from the target to the source graph. We call those matching graphs the source matching graph and the target matching graph. However, for the present paper, we only use the source matching graphs. To make this more clear, I'll best give a quick example of how a matching graph is built. So here on the top, you can see the example edit path from before, and I will explain to you now how the source matching graph is built. So we start by taking all the nodes that are substituted. Those would be the ones here, 1, 2, 4. And important to notice that all the nodes that are deleted or inserted are not in the matching graph. And then, as you can see, I've called this here pruned. This is because we also add some edge pruning afterwards, meaning, for example, the edge between here and here, that would be between node 1 and node 0 and 2, is not added in the matching graph. And the reason why is that it is only added when the edge also exists in the counterpart graph, in the target graph here, between the matching nodes, meaning because we matched here node 0 to 0 and 2 to 2, we only add the edge if it exists between here 0 and 2 in the target graph. And as you can see in the top example, it doesn't exist there, so we didn't add it. Okay, so as I have mentioned in the general idea, our idea is to use those matching graphs to embed a given graph into the vector space with the way that it is represented by a binary vector that contains 1 if a matching graph is contained in the graph and 0 otherwise. I will make this clear by an example. Let's say we wanted to embed G1 into the vector space, and we would have matching graph M1 and matching graph M2 and more matching graphs. So in this case, matching graph M1 is a subgraph of G1. So we would write the 1 here, and matching graph M2 is not a subgraph of G1, especially because of the Q here, so it doesn't occur in G1, so we would write a 0 at this spot. and so on. Next up, I will explain how we created the set of matching graphs that we finally used to create the vector embeddings. So we start by a given training set, in this example 3 graphs, and we build all the possible matching graphs for the given training set. And as I mentioned, we only use the source matching graphs from the edit path source to target graph. So in this example, one graph would be from the edit path G1 to G2. There would be this matching graph. Then we would have one from G1 to G3, and then G2 to G3, meaning we created 3 matching graphs in this case. And important is that we take all the graphs that we have so far, meaning the basic graphs and the matching graphs, and we put them in a set. Then next up, we pick a fixed number. In this example, the number would be 4, and we then randomly select 4 graphs of the existing set. In this example, you would select the G1 from the originals and the 3 matching graphs. And we would then continue again by creating all the possible source matching graphs for these combinations. So the first example I've written down, that would be the matching graph from G1 to matching graph G1, G2. And this would in turn yield a new matching graph. And the same procedure is done for all the possible combinations. Important to notice here is that the newly created graphs at each step are then added to this original set that contains so far these graphs. However, they are only added if they do not already exist in this set. We then continue to iteratively create the matching graphs by always selecting 4 random graphs of the already existing set, and we continue this iterative process until no new graphs are added to the set. Our approach is somewhat similar in spirit to other approaches like subgraph matching kernels, graphlets, or frequent substructure-based approaches, as these approaches also extract some information from a graph and then code it in a new sort of graph. However, our approach differs as it extracts information based on graphite distance and based on a pair of graphs. We evaluated our approach on 3 different data sets. One of the data sets would be the NCI1 data set. It has 2 classes of cancerous and non-cancerous molecules. It has categorical node labels and no edge labels. Here you can see some example graphs. Then similarly, the AIDS dataset, again 2 classes, confirmed active and confirmed inactive. It contains categorical node labels again and no edge labels. You can see 2 examples here. And lastly, the mutagenicity dataset, again 2 classes consisting of mutagen and non-mutagen molecules. The graphs again have categorical node labels and no edge labels. Now that I have shown you the data sets, I can also show you a few examples of how the matching graphs that were created look like. In order to do this, I will show to you an example of the NCI1 dataset of a set of matchings that happened in the process. So here on the top left, you can see a source graph, and here on the right, the target graph. Those 2 matched produced this matching graph. You can see that this matching graph is substantially smaller than the original graph. Then here on the same level, we had another matching that happened, which produced again this smaller matching graph. And then in the next iteration, the matching graph that was created here and the one here got matched again together, and they produced in the end this very small matching graph here. Okay, before we get to the results of the experiment, I will show you a small table that shows the relation of the number of training samples for the individual data sets towards the number of iterations used for matching graph building, the total number of matching graphs created, and the total number of matching graphs selected. On this slide, I will use matching graphs and features interchangeably, because after embedding a graph in the vector space, the matching graphs basically become features of ones and zeros. And for the feature selection here, we used a standard algorithm, which was like a recursive feature elimination based on feature weights of random forests. So what you can see here immediately is that, for example, for AIDS and mutagenicity, the total matching graphs created are much bigger in relation to the number of training samples compared to when we look at NCI1. However, the number of iterations for all of them is very similar. AIDS had 4 iterations until termination and the other ones only 3. And then when we look at the total numbers of features that have been left after feature selection, we can also see that is we have here a smaller percentage that is left compared to the NCI1, but overall on all data sets the feature selection trimmed quite a few features away. So for the experimental evaluation, we compared it to 2 classifiers. One of the classifier is denoted later as KNN-DBP. What it is a k-nearest neighbor classifier that directly operates on the graphite distance matrix denoted as DBP. Then the second classifier is support vector machine denoted as SVM-DBP, and it operates on a similarity kernel that is defined as follows. So it consists of the negative of the graphite distance matrix. We decided to compare our approach to these classifiers because our main idea is to improve graphite distance, and these 2 classifiers are commonly used with a graphite distance. Here on this table you can see the results. The circle here always indicates statistical significance of the improvement. You can see here the baseline for AIDS for the KNN is 89.6%, and for the SVM it is 99.4%, and our approach was 99.6%, which is better than both cases, however only statistically significant compared to KNN. Then for the mutagenicity, we have 2 statistical significant improvements over the baselines. And lastly, for the NCI1 dataset, we are statistically significant better compared to the SVM approach. We measured the statistical significance by a Z-score test. So that's it already. Let's continue with the conclusion. Our idea was to use matching graphs that are pre-computed on training graphs to then build vector representations of graphs by means of subgraph isomorphism. Each graph is represented as a binary vector that contains entries of ones and zeros. A given entry is 1 when a matching graph is contained in it, and 0 otherwise. And yeah, initial experiments show quite promising results. For the future work, as I already mentioned, we would of course like to compare our approach with other of the subgraph or graphlet based kernels and then combine our representation with some different and maybe more state-of-the-art classifiers. Thank you for your attention, and I will be looking forward to answering your questions during the live sessions.